Hi everyone, this is Kosti Vasilakakis and I'm a Global Business Development Manager from the ML services at AWS. Today, I have with me Stefan Natu, a Senior ML Specialist, and we want to help you and all other stakeholders from highly regulated industries like that of financial services develop a deeper understanding of how you can build end-to-end ML workflows with SageMaker while complying with your industry's legislation. Now, let's see what we're going to cover today. Today, we aim to address these 8 requirements, which we have consolidated from a series of financial services customers. We have put together a presentation and a Jupyter notebook so that we not only share best practices, but we also give you a hands-on, concrete, and end-to-end example from data preparation all the way to model monitoring. More specifically, we will showcase these 8 following objectives. First, how to deploy SageMaker in a VPC and achieve compute and network isolation. If you come from financial services, that's expected and no internet connectivity should be given by default. Second, how to authenticate only users that can be identified and authorize them appropriately based on their IAM permissions with no multi-tenants. Third, how to integrate with your private Git, code commit, or Artifactory as a common source of truth for transparency and versioning, as well as how to standardize notebook provisioning with lifecycle config. Fourth, how to encrypt data in transit and at rest with customer-provided encryption keys. Fifth, how to trace ML model lineage from data preparation, model development, and training iterations, as well as how to audit who did what at any given point in time. Sixth, how to explain and interpret the trained model by using sub-values and feature importance. Seventh, how to monitor your model in production to protect against data drift and automatically react to rules that you define. And lastly, how to reproduce the ML model based on model lineage and the stored artifacts. Here, we show the most common steps in an ML workflow, from data sourcing all the way to productization of the trained model, and we wanted to quickly set the expectations as to who we believe should help in satisfying each requirement and where we will be diving deeper today. The 3 most common personas that we have encountered are the first, the system operator or SysOps team that set the necessary security guardrails and enable the systematic access to the ML environment. Second, the data scientists that work from data sourcing and feature engineering to training a model, and then handing it over to the third persona, the DevOps engineers, or else the MLOps team that either uses an automated CI/CD pipeline for the deployments or goes through a manual productization process. There's of course other personas depending on the organization structure, and for example, in many organizations, data engineers are responsible for sourcing and performing ETL on the data, when data scientists only focus on the modeling and feature engineering. Today, we will showcase how we leverage a prepackaged workshop that helps SysOps teams enable secure and systematic access to SageMaker by the AWS Service Catalog, while complying with the 4 shown requirements. On that front, we will redirect you to the detailed workshop and just share some best practices. In today's demo, we will dive deep on the data scientist persona and what they need to do to comply with the above mentioned requirements. As you can see, data encryption is also mentioned here and in the SysOps responsibilities, and that's because both personas need to partake. Stefan, in a little bit, will walk us through the Jupyter notebook, which includes an end-to-end example of the areas that you see here in green, from data preparation to model development, all the way to triggering the deployment of the model, as well as the model monitoring. On each requirement, we will still give you best practices through the slides, but we will dive deep on the Jupyter notebook itself. The DevOps experience and requirements will actually not be covered today, but will be addressed through another demo that we're currently working on. So let's see the architecture and the ML steps that will be part of today's demo. In the demo, we will spin up SageMaker under a VPC with no internet access. We will use IAM to provide only the necessary access to a single user, and we will integrate it with a code commit repo. we will use AWS KMS or else Key Management Service to encrypt data at rest and in transit. And as every action is an API call, we will track all of them via CloudTrail, and we will use SageMaker experiments and code commit, which in your case could be an Artifactory, for example, for model lineage. In this example, we will pre-process raw data using a managed service called SageMaker Processing, which lets you easily run pre-processing, post-processing, and model evaluation workloads on a fully managed infrastructure. We will also use a custom container with XGBoost, which we will build within SageMaker, and we will deploy in the AWS Elastic Container Registry, or else called ECR. We will then use SageMaker's one-click training to scale our training job in a managed fashion over spot instances to reduce cost. And we will then save the trained model artifacts in AWS S3, which we will be able to use to showcase interpretability and explainability in the SageMaker notebook itself. We will then go through a manual model deployment process, which in a real scenario in the future demo will be a CI/CD pipeline that will automatically deploy the model. We will then deploy a monitoring job that you see here to evaluate if there are violations on the data type or significant data drift on the live data. And lastly, we will showcase how you can use SageMaker experiments and code commit or Artifactory to reproduce the exact same pipeline and model by the stored artifacts. As mentioned before, we leveraged a comprehensive workshop which can be found in the link here and helped us provision SageMaker via the AWS Service Catalog. That means that once a data scientist requests a notebook from the self-service portal, a CloudFormation script configures SageMaker to direct all networking traffic through an ENI under the customer's VPC, in which we can enable or disable the internet gateway that controls access to the public internet. In our scenario, we chose to disable the internet access for all SageMaker components, and more specifically, across notebooks, training, and hosting. We also use VPC endpoints to gain access to data in S3, as well as enforce KMS keys usage for all data. Once there is very detailed guidelines on the workshop, for completion purposes, I'll just spend 2 more minutes walking you through the best practices on the first 4 regulatory requirements, and then I'll let Stefan dive into the hands-on demo. As discussed, all SageMaker components should be deployed and accessed over the VPC with no internet connectivity. And the VPC endpoints should be used to control data traffic across the necessary AWS services. VPC endpoint policies can help you further control traffic, but you can also limit access to one or a couple IPs to enforce users to only go through the corporate network. And lastly, add subnets and security group IDs when you call a training from your notebook. Those are your VPC's subnets and security groups and can help in building the ENIs for you. In addition, for proper authorization and authentication, use IAM and tag-based access control to allow only one data scientist per notebook. That way, once you launch the notebook, your identity is attached as per the login through the corporate federated AD, and thus you can make sure only your name and ID can access it. As SageMaker runs on EC2, it also inherits the same IAM roles which follow the same access patterns. With that, use IAM condition keys to make sure that, for example, when a user tries to instantiate a training job, they have indeed given the necessary subnet and security group parameters that I just mentioned. And lastly, use detective controls to detect and terminate immediately if a user is not following the best practices and launching resources under the subnet. With regards to artifact management, remember that apart from building the models in SageMaker, you need to manage both the training and inference Docker containers. All these need to be managed using a centralized artifact management or dependency management system. For version control, you can use the AWS Code Asterisk product suite, and any GitHub commands directly from SageMaker notebooks. For the repositories management of Docker containers, model artifacts, and Python or R libraries, you can use Amazon S3, Amazon ECR, or Artifactory. In addition, use lifecycle configurations to distribute common libraries your team uses, and they're not available by default in the SageMaker instance. You can actually use lifecycle config for both when you create a notebook as well as when you start a notebook. Lastly, as for model artifacts, which are saved in S3, we recommend that you enable S3 versioning to track all versions. On the data encryption front, it is important to note that SageMaker has encryption of data at rest and in transit built into the service. For the data stored in S3, it follows the exact same best practices that S3 comes with, meaning that you can use your own customer managed keys to encrypt and decrypt your data. Exactly the same occurs for the EBS volumes that are used on the notebooks, on the training jobs, and on the hosting instances. Lastly, for the training containers that support cluster mode like TensorFlow, for example, the traffic between training nodes can be encrypted, but you have to remember that it actually might downgrade your performance. Now, I'll hand it over to Stefan that will walk us through the secure environment we instantiated to the CloudFormation script, as well as the Jupyter notebook with the end-to-end ML walkthrough that covers all 80 requirements. Once he is done, I'll wrap it up and walk you through the best practices on the last 4 objectives. Stefan, here you go.
Thank you, Kosti, for that high-level explanation of the best practices for the first 4 compliance requirements on compute and network isolation, authentication, artifact management, and data encryption. Now I will dive deeper and walk you through a demo showing the end-to-end data scientist experience on Amazon SageMaker using familiar Jupyter notebooks. As a best practice in most regulated industries such as financial services, data scientists are typically not allowed to create notebooks, provision or modify elastic network interfaces or ENIs, or provision any underlying instances. This can be done using infrastructure as code best practices by administrators. As Kosti mentioned, here we have used CloudFormation and the AWS Service Catalog to already provision a secure environment for data scientists to work with. This script is available as part of the security workshop we leveraged, but will also be available in the GitHub repo associated with this notebook. So let's jump right into the console. To pre-create notebooks, we can use the Service Catalog. Data scientists can simply click on Launch Product, and the appropriate product, such as a SageMaker notebook environment, can be provisioned for you. Notice that we have also created an IAM role for our data scientists to assume, which will only allow them access to the services that they can use. For example, while data scientists can access the SageMaker console and open Jupyter notebooks, data scientists should not have any permissions to access services such as IAM or AWS KMS to modify any of the underlying roles or permissions or create or delete any access keys that are granted to them. Data scientists should also typically not be able to access any developer tools such as code commit, code build, code deploy, or code pipeline that could potentially be used to deploy models into production. However, data scientists can have access to the code commit APIs, as we shall see later, in order to push and pull code into the appropriate repositories or branches. This ensures that administrators can enforce least privilege access to AWS services. Let's now take a look at the SageMaker notebook environment that we have pre-created using the Service Catalog. Before jumping into the notebooks, let's take a quick look at the notebook environment that we have pre-created. We have provisioned a T3 instance, which is sufficient in many cases for data exploration within the notebook. Attached with it is an encrypted EBS volume to ensure data encryption at rest. We have also used lifecycle configurations to pre-download any open source libraries or any datasets. Let's take a quick look at the lifecycle configuration script attached to this notebook. Here, we are pre-downloading a dataset that we are going to use for data exploration and for training models. In addition, we're also installing using pip open source libraries such as SHAP that we shall use for extracting feature importances. In order to maintain network isolation such that the VPC that is connected to the data scientist account does not have internet access, this can be done using a private PyPI server or a pip mirror from a centralized IT or a shared services account, which in turn does have access to the public internet. In addition, we have attached a code commit repository with appropriate secrets that has been attached to this notebook for versioning any code. Note that while we denied data scientists access to the code commit console, access to specific APIs for getting, pulling, and pushing code from the repos has been granted. Enterprises can replace code commit or Git with Bitbucket or their own on-prem enterprise Git repo. For this demo, however, we shall be using a code commit repository to check in and check out any code. Finally, in order to maintain network isolation, we have automatically disabled any internet access from this notebook, and we have attached a security group and the proper subnets in order to control the ingress and egress of network traffic to and from our notebooks. System administrators can now monitor the network traffic for API calls using tools such as AWS CloudTrail. Let us now take a look at the notebooks that we have built for our data scientists. In particular, to illustrate the separation between data scientists and engineers, I have created two notebooks to demonstrate the typical data scientist workflow and a second notebook to demonstrate the model deployment and monitoring workflow. As Kosti mentioned, we shall not be demonstrating how to automate the DevOps workflow in this video, and we leave that for a separate video. So here I am in a SageMaker notebook environment that we have pre-created for you for the purposes of this demo. Throughout these two notebooks, we will demonstrate the 8 key concepts required for most regulatory industries to build ML workflows and how to ensure and implement them in the SageMaker environment. So let's get started with the data science experience. The first thing we want to take a look at is network isolation. To test our network isolation, as we have said earlier, we have disabled any internet access either from the Amazon VPC or from the private VPC that this notebook is attached to. To test this, let me go ahead and run this curl command. And as we see, the command does not run, indicating that we have indeed disabled internet access from both Amazon and the custom VPC that's been attached to this notebook. Next, let's take a look at authentication and authorization. In addition to attaching a role to the data scientists, SageMaker notebooks also need to assume an IAM role in order to be able to access APIs such as the SageMaker API, Code Commit APIs, or access data in Amazon S3. So let's take a look at the IAM role that we have attached to this notebook. The first thing we notice about the IAM policy that has been attached to this notebook is that we have granted SageMaker full access. This is generally not a best practice. For example, if data scientists in your organization do not put models into production directly, they should not be granted access to create SageMaker endpoints or ENIs. However, they may need access to SageMaker batch transform for validating their models against a batch of data. Also notice that we have granted full access to Amazon S3. Fine-grained access control to Amazon S3 can be ensured either using IAM permissions on the SageMaker notebook or using bucket policies, as we shall see later on in this video. Having addressed IAM and networking, let's now go ahead and import the libraries and utilities that we will need throughout this notebook. In particular, in order to be able to track the metadata associated with our training jobs as well as our processing jobs, we are going to load in SageMaker experiments. Additionally, we're also importing the KMS key as well as the network configuration settings that we will need in order to ensure that any network traffic traverses private link and does not traverse the public internet. Finally, in order to manage our artifacts, we are going to import the names of the buckets that have been created along with this demo for us to use. Let's jump into one of the buckets and let's take a look at the policies that are attached to it. So here I am in the data team bucket, which I'm going to use for storing any training data, test data, or validation data. Let's take a look at the properties associated with this bucket. The first thing we see is that as required by a lot of our regulatory, highly regulated industries, we have attached default KMS encryption with this bucket. Additionally, in order to control the ingress and egress of traffic to this bucket, we can control this using fine-grained bucket policies. For example, this bucket has a policy which denies any get or put objects from any principal unless they emanate from the source VPC endpoint that we have created. This ensures that all network traffic to and from this bucket only traverses private link and will not traverse the public internet. Further fine-grained access controls can be applied to the S3 buckets directly or to the SageMaker IAM role that we demonstrated above in order to ensure that the data scientists only have access to the buckets that they should have access to. This can also be done using tags attached to IAM roles to ensure that different sub-teams within a larger data science team, for example, can only access certain buckets. Having imported the necessary libraries that we need for our demonstration, let us now move into the next stage, which is on pre-processing and feature engineering our dataset. The first step in any data science lifecycle is data exploration, pre-processing, and feature engineering. Here, we have used a credit card dataset to predict whether or not a user will default on their credit card payment based on historical payment data, historical bills that they have received, as well as some demographic information about the user. As we can see, this is a binary classification problem where we want to predict the default probability for whether the user will default on their payments or not. Typically, once we import the dataset, we want to do some simple data exploration, such as we want to look for any missing labels or we want to look for any missing values in our features. We also want to see if our labels themselves are actually imbalanced. In other words, whether there are more of one label in our dataset than the other. This is indeed the case here. For example, we can see that there are more users that have not defaulted on their payments versus those that have. Another thing that's important to look at is to look for correlations amongst our features or our independent variables themselves. For example, we see here that the payment histories and the bill payments are actually correlated with each other. If we were to use a simple model like a linear regression, we may want to consider a technique such as principal component analysis to decorrelate some of these features or some other dimensionality reduction method in order to remove some of the correlations that we have in our independent features. Having explored the data, we can now pre-process our dataset. This typically involves steps such as outlier removal, transformations such as one-hot encoding of categorical variables, and splitting of the data into train and test or validation. This can be done in small datasets directly within the SageMaker notebook environment itself. However, this is not really a scalable method for larger datasets. However, customers can now use SageMaker processing to pre-process their data at scale. SageMaker handles the provisioning and the setup of the underlying instances that you need in order to prep your data, runs the pre-processing job on those instances, and automatically deprovisions the instances so you stop paying for them once your processing job is complete. SageMaker currently provides managed containers for your scikit-learn code, which is the most common pre-processing library. But customers can also bring their own containers, for example, to run pre-processing jobs on Spark or on Dask. To see how this is done, we first call the scikit-learn processor API and provided an instance type that we're going to use for our pre-processing job, as well as a count of the number of instances that we want to use. Additionally, we also provided the KMS key to ensure that any EBS volumes that are attached to this instance are encrypted, so we have data encryption at rest. We also provide the network configuration settings that we defined above in order to ensure that the network traffic only traverses private link and does not traverse the public internet. The next thing we want to do is we want to take the same code that we had above, but now we want to package it into a Python script. This is done here. Once we package our code into a Python script, we simply upload that code to an S3 location. We provide the locations for the training and the test data, and we're ready to run our processing job. To run the processing job, we simply call the scikit-learn processor.run command, providing it the location of our source code, as well as our source data and the destinations where we want our train, validation, and output datasets to be stored. We also provide any other arguments that we might need in order to run our script, such as the train test split ratio. Here we choose a standard train test split ratio of 80-20. Once that's done, SageMaker processing takes care of setting up the instances, running our code, and then deprovisioning those instances or tearing them down as soon as the processing job is complete. We now have our train and test data sitting in the S3 buckets that we specified. Let's go take a look. So here I am in the bucket that I'm using to log my data artifacts, and what you can see is that a number of different folders have been created after running the processing job. For example, we have a folder for holding the training data, the testing data, as well as the training data with the headers included, which we will need later in order to run our model monitoring jobs. Let's take a look at one of these folders. So here we have a CSV file that holds our training data that we are now going to be using for training our machine learning models. Before getting into our model training, let's take a quick look at traceability and auditability. Most regulated industries have requirements around tracking metadata associated with the training jobs. Additionally, if different data scientists, for example, run multiple models on the same data, or the same algorithm with different hyperparameters, they want to be able to compare their training runs to determine the best model to deploy. SageMaker Experiments helps us do this. It automatically tracks the metadata associated with training jobs, as well as any other jobs that are related, such as our pre-processing job. Although we do not demonstrate this here, with SageMaker Studio, we can view all of our training runs in a single pane of glass view, compare them, as well as do any custom plotting, comparing these runs against different metrics. Here, we will demonstrate how to call the SageMaker Experiments APIs directly in the notebook environment and visualize the outputs in the notebook. The first step is to call the SageMaker Experiments API and create a SageMaker experiment with a suitable name and a suitable description. Next, we want to be able to track jobs that we have run previously, for example, the pre-processing job that we just ran. In particular, we want to log certain parameters such as the train-test split ratio, potentially also any random seed parameter that we used in order to generate our train and test splits, such that we have reproducibility. We also want to be able to log, for example, the locations of our raw data, our train data, and our test data, so that this can be used later for auditability. Having now logged our pre-processing job, let's take a look at how we can run model training in Amazon SageMaker. There are, in fact, multiple ways to run model training in Amazon SageMaker. For example, customers can choose from 17 built-in algorithms to train from, such as XGBoost or Linear Learner. Additionally, they can also bring their own scripts that are written in popular frameworks such as TensorFlow, MXNet, or PyTorch. They can also bring their own containers, and SageMaker can run the training job directly on those containers. Here, we will demonstrate this latter aspect, as a lot of our customers already have their code packaged into containers that they're currently running on-prem. We have written a training script using XGBoost, which is available in our GitHub repo. And as a first step, we're going to put our code and all of its dependencies into a Docker container and upload that Docker container into ECR. And that is what this code snippet here is exactly doing. Once our code has been successfully uploaded to ECR, we are now ready to train our machine learning model. The first thing we want to do is we want to log our training job as a trial. This way, different experiments different trials, i.e. different training runs that are conducted by different data scientists, or maybe even the same data scientist on the same dataset, can be logged under that experiment header that we created earlier. Think of experiments as a folder that tracks all of your metadata associated with your different experiments, and the trials are the different files that you put into that folder. We are now going to add our pre-processing tracker earlier to the trial component, because that pre-processing job in fact led to the trial training job that we are about to run. Having now created the trial, we can now create the SageMaker estimator object. The first thing we need to do is we need to point the SageMaker estimator to the Docker image that we just created above. Secondly, we need to specify the instance type where we want to run our training job, the amount of time we want to wait for our training job to run, and the output path where we want to store our model artifacts. A key advantage of using Amazon SageMaker for machine learning training is that we can save up to 90% in cost by using spot instances. we simply need to set the train using spot instances flag to be true and specify a maximum amount of time we're willing to wait for a spot instance to become available, and SageMaker will take care of the rest. As before, as we saw in our pre-processing jobs, in order to ensure that any network ingress and egress of traffic occurs through private link, we provide the subnet IDs as well as the security group IDs that we're going to be using to ensure our traffic is secure. We're also going to provide a KMS key to encrypt any EBS volumes that are attached to our training instances. Note that Amazon SageMaker takes security extremely seriously and has all of the best security best practices already put into place. For example, different training jobs are isolated on different instances in Amazon SageMaker. Additionally, by using security group level isolation, we can ensure that different jobs that are running different models do not have any way of communicating with each other. If multiple instances, however, are running the same job, for example, if you're running distributed computing, you can use the encrypt intercontainer traffic flag and set that to equal true to ensure that any data in transit is also encrypted between our training containers. Here, since we're only using a single instance to run our training job, we set that flag to false. However, we do have this option to set that flag to true if we do choose to run distributed training on a much larger dataset. Having created our estimator, we can now specify the hyperparameters that we're going to be using to run our XGBoost model. We provided the training input, which is the location of the training dataset that we saw earlier. We create an experiment config where, as we call the fit function, we provided the trial name where we want to log this particular trial run, and we give it a prominent display name such as training. And now we're ready to kick off our training job. And as we can see, SageMaker takes care of our training run for us. But a key thing to notice here is that while our entire training job in fact took about 83 seconds, we were only billed for 32 of those seconds. In other words, we have managed to save over 60% using spot instances. As such, using spot instances is always best practice wherever possible to run your training jobs. Having completed our training, let's take a look at what the Experiments API has tracked. We can do this by calling Experiment Analytics and specifying the trial name that we used for our training job. We can plot the results in a data frame, and as we can see, the SageMaker Experiments has managed to track our pre-processing job as well as our training job. Let's dive a little bit deeper into what our training job was able to log. This can be done by calling the describe trial component API and specifying the trial component name to be the name of our trial component associated with our training job. And the first thing we see is that our SageMaker Experiments has logged all the metadata that's associated with our training run. For example, it has logged whether our training job was completed or not. It has logged the start time and the end time, as well as the creation time for that training job, and potentially also who created that training if we chose to specify a name here. It has also tracked parameters such as the location of the Docker image that was used to run our training job, as well as any metadata associated with the instances that was used to run our training. It also tracked the hyperparameters that we used to run our training jobs, as well as other artifacts such as the location of our training data and the location of our model outputs, where our model artifacts are stored in a tar file. Finally, if we choose to do so, we can also log any custom metrics and have those be tracked using SageMaker Experiments. These custom metrics can then be used to compare different training jobs against one another. Finally, we want to take a look at model explainability with SageMaker. Explainability is a key regulatory requirement and often dictates the model choices for models that can be put into production. For tree-based models such as XGBoost, we can either use the built-in APIs that will extract feature importances, or we can use a library such as SHAP to obtain feature importances. All we need to first do is we need to pull in the model tar object from our Amazon S3 bucket into our local notebook environment where our SageMaker notebook is hosted. We have written some custom utilities to do this that are not shown, but will be available in the GitHub repo associated with this notebook. Once we have pulled in the model source files, we can now unpack the model and we can see that indeed we trained an XGBoost classifier. We can now use the built-in scikit-learn libraries to extract and plot the feature importances directly from this XGBoost model. Additionally, we can also use a library such as SHAP. SHAP values can be calculated by computing two models, one with and one without that feature included, and comparing the model outputs to assign an importance value to that feature. This can be done by calling the tree explainer API on the model and providing it our dataset in order to extract the SHAP values. Once the SHAP value calculation is complete, we can plot a summary plot either in the form of this bar graph that's shown here or in the standard summary plot format that is provided by the SHAP library to extract the relative feature importances of our different features. This now concludes the data science portion of our demo. In particular, we have covered security. We have covered notebook network isolation, as well as network isolation during training and processing. We have covered encryption of data at rest and in transit. We have covered data pre-processing using SageMaker processing. We have demonstrated how you can use a BYO container approach to train your machine learning models, as well as achieve cost optimization and cost savings with using spot instances. And finally, we have shown how you can use SageMaker experiments to track the lineage associated with your model down to any data artifacts, as well as any model artifacts and model parameters and model metrics that are used or generated during your training job. And finally, we have demonstrated explainability and interpretability using SHAP values. Once the training job is complete, data scientists will typically upload their code to a code commit or Git branch for review. Once the code has been checked in, it can be tagged. Different tags can be viewed for any associated metadata as shown here. For example, we have specified a tag version 0.1 to our data scientist workflow notebook that we demonstrated earlier. If we call the git show API, we can see all the associated metadata associated with that particular commit. For example, when that commit was made, what was the message that was attached to that commit, what was the IP address that was used to make that particular commit, as well as the details associated with the code that we committed. Later on, we shall also see how we can track this tagged metadata using SageMaker experiments as well. Here, the code will now undergo unit testing, build testing, and any other QA tests that are needed. Models might also undergo a human-in-the-loop review to check the model outputs, the feature importances, etc. Once the code has passed any necessary reviews, we are now ready to move to the model deployment and monitoring portion, which is typically done by a data engineer or by DevOps engineers. For simplicity, we will continue to demonstrate this in the context of a notebook environment to demonstrate the model deployment portion of the workflow. In this notebook, we demonstrate how to manually deploy a DevOps workflow by taking the model that we trained in the previous notebook and deploying it into production and monitoring the model endpoint. First, we will need to load in necessary libraries that we need to deploy our model, as well as run any monitoring jobs that we are going to run on our endpoint. We will also import the network configurations as well as the KMS keys that are needed to enforce security guardrails, as well as the bucket name where our model artifacts have been stored. The first step then is to create a model object by providing it the location of our inference container that contains our inference or serving script, as well as the location of our trained model artifacts which contain the weights that are associated with our model. We also provided the VPC configuration to let Amazon SageMaker know to create an ENI for model hosting. Since we now want to monitor our deployed models for any data drift or any concept drift that might be associated with the changing relationships between the features and the labels in our incoming dataset, we are going to use a data capture configuration. The first thing we need to do is set the enable capture flag, which by default is set to false. We need to change that default setting to true. We also need to specify a sampling percentage. For the purposes of simplicity here, we choose to sample all of the inference requests that are sent to our endpoint, and we provided an S3 capture path where our sampled served requests will be stored. Next, we create an endpoint configuration where we specify the instance type that we use to deploy our model and the number of instances that we want to use. We can also choose an A/B testing scenario where we can route a part of our traffic to a different model. However, in this case, since we only have a single model that we're deploying into production, we're going to send all of our network traffic to that model, and we're also going to specify the data capture path that we had specified earlier. Now we are ready to create our endpoint. SageMaker will manage the task of creating an HTTPS endpoint for us that can serve inference requests to a client application. Let's test that this endpoint has indeed been created as this creation ARN shows. The first thing we can do is we can call the real-time predictor API, and we can provide it a sample from our test data. So in this case, we're just pulling 10 rows from our test data in this testsample.csv file, and we're calling this predictor.predict API by passing it the payload from our sample dataset. And if this can predict successfully, then we should see a done command after all of the predictions have been run. And indeed, that's what we see here. So let's now take a look at the captured data outputs. We first see that the inference outputs have been stored in the form of a JSON lines formatted file in Amazon S3. Let's quickly navigate to that bucket where those outputs are stored. As before, we want to manage the security of that bucket by enforcing things like encryption at rest, as well as stringent bucket policies. Since we're using the same data team bucket in order to store our model monitoring outputs, or our data capture outputs in this case, we shall not demonstrate those encryption at rest as well as those bucket policies earlier, as we have already done that. We see, however, that the data capture config creates a folder in our S3 bucket called monitoring. If we investigate this deeper, we see that it has logged a folder under the name of the training job or the endpoint configuration or the endpoint that we used for that particular model. We have chosen to log all the traffic, and now we have specific folders associated with the actual timestamps where those inference requests were sent. If we navigate to one of these folders, we indeed see that we have the inference requests in the form of this JSON lines format. Let's now jump back into the notebook and take a look at one of these inference requests and see what it looks like. Here we see that our data capture config has actually captured both the input that was sent to our payload or to our endpoint, as well as the final output. In this case, our model predicted that the transaction itself, that the individual would not default on their credit card payment based on these inputs that were sent to the model endpoint. This can be used for model monitoring to ensure that the endpoints or that the features that are being sent to our model for inference are indeed the correct ones that the model was actually trained on. Most client requests to endpoints will not be made via notebooks. To demonstrate the typical separation between API requests and model endpoints, we have used API Gateway and a Lambda function that is sitting in our private VPC in front of our endpoint to let external client applications send API requests to our production model. This could be a situation for online inferencing. For example, where someone swipes their credit card at a store and that transaction is approved or denied by first calling an ML model that ensures that the transaction isn't fraudulent. To demonstrate this, we have placed our API gateway behind an internet-enabled VPC and have used Postman to send in API requests to the model. For example, I'm sending this data payload to the model, and I'm going to click on the send button here. And when I do that, I get an API output that was very similar to the output that we saw from the data capture configuration before. For example, we see both the input data that we sent to the model as well as the output that was generated by the trained model. Now, for internal requests that are made from internal clients, this can all be done within an internet-disabled VPC. Now that we have successfully deployed our model, as well as captured the inference data, we are ready to monitor our model. Model monitoring is a service for checking our deployed endpoints against data or concept drift from incoming data, in particular to notify administrators or engineers of any performance degradation associated with our models, as well as when it may be time to retrain the ML models. In order to do so, First, we need to specify the buckets where our monitoring outputs will be stored. Let's take a look at this particular bucket that we have created for storing our model outputs. Here we have the bucket that's storing our model monitoring outputs. As before, we want to ensure that this bucket has default KMS encryption to ensure encryption of data at rest, as well as bucket policies that are attached to it that enforce a VPC endpoint in order to control the ingress and egress of data in and out of the bucket. Having specified the locations where we want our monitoring jobs to store their outputs, let's now start a baselining job. SageMaker will automatically handle the provisioning of the underlying instance that is required to run the baselining job, but we need to provide it the instance type as well as our training data with the headers that we created earlier. SageMaker uses the DQ library to extract statistics from the data. The DQ library is available for customers to use and can be found on this link that customers can use to peruse the library as well as the source code in greater detail. Let's now see what the baselining job has extracted as the baseline for our data. Notice that the baselining outputs are located in this particular output folder, which is in the same bucket that we demonstrated earlier with the prefix baselining/results. Let's go take a look. So here I am back in that model team SageMaker demo bucket, and I have a prefix under the SageMaker demo. I can click on the training job that's associated with this particular endpoint, and you see that the folder baselining is located here. If I now look at the results subfolder, I see that I have a constraints.json and a statistics.json file that was created for me after I ran the baselining job. Let's now go back to the SageMaker notebook and take a look at what these JSON files look like. So here we have the statistics.json file, and we see that for each of the features as well as the labels, this file has inferred a particular data type as well as extracted some common statistics associated with those particular features. For example, the number of missing values, the min and the max, the standard deviations, etc. All these additional statistics are visualized here in a data frame format for customers to look at in greater detail. Additionally, it has also extracted some constraints that it's now going to look for. In particular, it's going to look to see whether certain features are allowed to be non-negative or not. And we can see that while certain features are indeed not allowed to be non-negative, others are in our training dataset. And any violation against these, for example, will be flagged by the model monitoring service. It has also inferred the data types that are associated with those individual features. Once the baselining job is complete, we need to define a monitoring schedule to run the model monitoring. This can be done hourly, weekly, or daily, and for this demo, we're going to choose an hourly cadence. We are also going to let Model Monitor know to publish metrics to CloudWatch. This can be used to generate CloudWatch alarms that notify administrators or engineers of any model performance degradation. Once we create this model monitoring schedule, we can generate some artificial traffic for the purposes of this demo. In particular, we are going to flip the signs on two of our key demographic features and store this fake dataset in S3. And we're going to invoke our endpoint constantly with this bogus data. So here we see that indeed our model monitoring schedule has been scheduled as expected. And we are now ready to look at some of the model monitor outputs. The first thing you might see when you call the model monitor list executions API is that initially you might find that no executions were found for that particular schedule. And the reason for that is that we have kicked off an hourly schedule, and therefore the model monitoring jobs only run on the hour with a 20-minute buffer. So we may have to wait for a while before we see an execution to happen. However, after some amount of time, indeed, we should start to see some metadata associated with the monitoring executions. In particular, the model monitoring service will track things like the locations of the constraints file as well as the statistics file that was used to generate any violations. It will also track the instance types that were used to run that particular monitoring job. It'll track whether CloudWatch metrics have been, whether published CloudWatch metrics has been enabled. And it'll track the status of that monitoring job. And in this case, the processing job status has been completed, and indeed it has been completed with a particular violation being found. Now, if you run this command over and over and you let the monitoring jobs happen on the hour, you might find that more and more violations have been found with your data. So let's take a look at one of these violation jobs that we found. Here we see that the model monitoring service generates a report. That report is located in our S3 bucket from earlier with the prefix /reports. So let's go take a look at that. So here I am back in that S3 bucket from earlier. And indeed, I have this reports folder. So if I look at the reports folder and look at the reports associated with my training job, I have my model monitoring schedule from before, and then I have folders that are based on the timestamp that's associated with when that model monitoring job ran. And here we see that we have that same constraints file and statistics file from earlier, but now we have a new file that has been populated here, which is our constraints violations.json, which captures the violations that we have found against those constraints. Let's now take a look at what one of these files looks like in our SageMaker notebook. So back in our SageMaker notebook environment, we can parse one of these JSON files, and let's take a look at the outputs. So here we see that our monitoring job has detected some baseline drift from our baseline for a number of different features. But in particular, the largest baseline drift was detected for the two features where we decided to flip the signs to minus of their values from before. And the largest drift was observed for those particular two features. As a final requirement, most regulated industries have is reproducibility. This means that they would like to log all the metadata that's associated with our endpoints and our trained models. In particular, compliance requirements may dictate that you not only need to track the lineage of your endpoints down to the raw data level location and the metadata associated with your raw data, but actually also down to the code level where the code that was used to train and deploy your models has been tracked by the source or version control tools that you're using. Here, we can use the familiar tracker API from SageMaker experiments to track the metadata associated with the Git commits from our source code and our deployment code that we have just shown. Not shown in this demo is that I have gone ahead and uploaded the code that generated this particular notebook to the private code commit repo that I've created. I've also written some code here that pulls from the code commit APIs any metadata that's associated with the notebooks that I have committed. I can now visualize this in the SageMaker experiments using that experiments analytics API from before. And here we see that we have now captured the end-to-end data scientist as well as the DevOps workflow in this particular data frame. Indeed, we have captured the source control lineage using SageMaker experiments. We've captured the author name as well as the commit ID that was associated with that particular commit, any message or any date and epoch format that was associated with that particular commit. We have tracked our pre-processing job. We have logged our training job, as I showed earlier, with all the training metadata, for example, the instance types used to train the model, the hyperparameters, potentially the model metrics as well, if we choose to do so. And finally, we have also tracked the production endpoint lineage. For example, we have tracked the author name as well as the commit ID associated with the code that led to the production deployment of the production endpoint, as well as any messages and timestamps for when that code was deployed into production. This now concludes the manual deployment or the DevOps workflow that we wanted to demonstrate from the SageMaker notebook. So let's recap quickly about the various things that we have demonstrated in this notebook. In particular, we demonstrated how to securely deploy a trained model using the same network configuration as the data scientist portion of the workflow. We have demonstrated auditability and reproducibility by using SageMaker experiments to track the lineage of our processing jobs, our model artifacts, as well as the Git commits that are associated with our deployed model endpoints. We have demonstrated how to deploy a model endpoint and how to query that endpoint or send inferences to that endpoint, both from a SageMaker notebook as well as using an external tool such as Postman. We have set up model monitoring, and we have demonstrated how we can monitor our models in production for any data or concept drift. I will now pass it back to Kosti, who will give us the best practices on the last 4 objectives that we set at the beginning. Thank you very much for watching this demo.
Thank you, Stefan. Truly fantastic demo, thank you. As you said, I'll wrap it up today by giving you the best practices on the last 4 objectives we stated at the beginning. On the traceability and auditability front, all SageMaker API calls, as well as the S3 data events, are being tracked by CloudTrail, and you can audit them anytime. Also, all Jupyter logs are sent to CloudWatch, where you can set triggers for automated responses to any state changes. And lastly, as shown in the demo, do leverage the SageMaker experiments and your version control system to achieve end-to-end traceability of the metadata of the processing job, the training job, and the code behind the deployed model. On the explainability and readability front, as Stefan showed us, you can quickly address regulatory audits by visualizing and saving insightful metrics like feature importance and sub-values right from your notebook, just by calling the feature importance function or by installing the sub library. The exact same outcome, though, can be achieved by using the SageMaker Debugger API, which supports XGBoost. On the real-time monitoring front, remember that you can monitor at any frequency, not only the built-in algorithms, but any other container that you bring. In addition, apart from the built-in rules, like completeness check or data type check that model monitoring comes with, you can define your own rules that will automatically check for. And lastly, do you use Lambda functions to automate retraining based on the CloudWatch metrics that model monitoring emits, or even immediately stop the inference endpoint depending on the violation type or the data drift magnitude? Last, but certainly not the least, on the reproducibility front, once you have enabled SageMaker experiments and your version control system, you can track all the lineage of the model version that was deployed, and thus rerun the same pre-processing pipeline on the same data and then use the same model with the same hyperparameters. Of course, do remember that due to the randomness entailed in the optimizer implementing stochastic gradient descent, exactly same process and artifacts might have slightly different prediction outcomes. And to wrap this up, we hope we managed to address some of your key questions on how to build compliant machine learning workflows with SageMaker, and we'll be happy to stay in touch about any additional questions. Feel free to review the GitHub repo that contains the notebook Stefan just walked us through, and do reach out to our emails shown here with the handles if you need more help. Thank you very, very much for your time, and looking forward to hearing from you.